Hello there everybody, and welcome to another MCAT ACE lecture. And in today's lecture we're going to be covering a bonding topic. Specifically, we're going to take a look at hybridization of orbitals. So when we get into this, sometimes this is referred to as valence theory. So you may hear me interchange the terms hybridization theory or valence theory. And hybridization of orbitals is when we take two types of orbitals, for instance an s and a p orbital, and they combine together in order to create a hybrid orbital or an sp orbital. Now, when we deal with hybridization, this is one theory of many that can help us explain bonding and what's going on in terms of sharing of electrons and transfer of electrons and things of that nature. So when we look at bonding in terms of a subject as a whole, there's going to be a lot of other content that you're going to see not covered in this specific lecture, such as MO theory, which stands for molecular orbital theory. That's another theory that helps to explain bonding. How to draw proper Lewis structures, the idea of resonance. You'll also see things regarding bond length and sigma versus pi bonds. We will talk somewhat about sigma and pi bonds here when we deal with hybridization. But my point is there's a lot of content that is going to encompass the idea of bonding, because that's the way that we connect atoms and make molecules. So it's a very deep subject. It's far too much to put into one lecture and say this is the lecture for bonding and we're going to teach you everything about bonding here. So this lecture is going to focus specifically on valence theory, which is how we propose that orbitals hybridize in order to create covalent bonds. Now, some of the stuff we're going to look at in this lecture. Hybridization, again, I'm going to sometimes use the term valence theory. Again, valence being the outermost electrons that we're dealing with. Those are the ones involved in bonding. And specifically, why do we see hybridization occurring? Why do we propose that hybridization might occur? And that really has to do with orbital overlap. So when you want electrons to be shared, the orbitals need to overlap with one another, and that's going to be important. And then you're going to deal with the energy of bonding. So we're going to take a look at, if you recall from general chemistry, you've got 1s, 2s, 2p, and as we climb up the ladder, we continue to hike up the energy of those electrons. And so hybridization has some beneficial effects on the energy of those electrons. It brings it down a little bit, which is a good thing when we're trying to promote bonding and stability of the molecule. So we'll take a look at the various types of hybrids and their molecular geometry. Sometimes people refer to this as sp², the abbreviation, which deals with valence electron repulsion theory. That's the sp² theory. And we're going to see, we'll focus on a few of these here. Tetrahedral is a big one, especially because in organic chemistry, carbon will most often take up a tetrahedral formation. That's not to say it won't take up other formations, it certainly will. But it's one of the most common formations that you can have is a tetrahedral carbon. And these are dealing with sp³ hybrids. So the 3 is referring to the number of p orbitals being brought into the hybridization process. So keep in mind, anytime we're dealing with a valence shell, you're going to have one of your s orbitals, and there's 3 different p orbitals, px, py, and pz, because they have 3-dimensionality. Whereas if I think of an s orbital like a sphere, it's going to be, when I say not, it is 3-dimensional, but it doesn't have the spatial direction that I could get from those p orbitals that look more like figure 8s or dumbbells. A sphere is a sphere, and so when I turn it in any direction, it looks the same. I don't get any sort of difference from it. Whereas the barbell, if I'm holding it on one axis versus another, for instance, think of a graph x and y, I can see the differentiation in that. And so we're going to deal with up to 3 p orbitals, but there's only one s orbital. So again, sp³ is referring to a hybrid state in which the atom is bringing 3 of the p orbitals, meaning all the available valence p orbitals, into the hybridization process. In a trigonal planar or a flat molecule, we start dealing with sp² hybrids. This will happen very often when you have pi bonds or pi electrons, and those pi electrons must reside in p orbitals. So we'll take a look at trigonal planar molecules and what's involved with that. Then finally, we'll take a look at linear as far as the general sp hybrids go. Linear is going to be involved in things such as carbon dioxide or any other type of molecule that would have that straight line type of geometry. This will very often come up in triple bonded molecules, or if an atom has double bonds on both sides. So if an atom is involved in two double bonds, it will very often be a linear molecule. And these hybrids only involve one p orbital being brought into the hybridization process, and hence the term sp when we're dealing with that. Okay, then I'll show you, after we go through those, a very simple kind of cheat rule or cheat method to help you figure this out. It's called the n-1 rule. You have to understand what electron domains are, so we'll talk about that. It's basically any source of electrons that you can count around an atom. So when I'm looking at an atom, if I find a lone pair, that's one electron domain. If I find a bond, that's an electron domain. Even a double bond counts as one electron domain because those pi electrons and the underlying sigma electrons occupy one domain or one space around that atom. So if you can count those up, there's a very easy way to get to your hybridization, but we do want to understand some of the underlying theory before we sort of just pass it off and say, hey, here's the cheat rule, let's use it all the time. But certainly to save time on the MCAT, we want to have a rule handy that we can utilize. Okay, then we're going to take a look at briefly, because it tends not to be covered in quite as much detail until you're much higher chemistry classes, such as advanced inorganic chemistry. But we will talk about hybrids with d-orbitals for a moment or two. D-orbitals are a little more complex in their nature. They don't occur very often in organic chemistry. Now, the reason I say that is because in organic molecules, we normally have hydrogen, which is in the first quantum level, and then we have the most common of them are carbon, certainly, nitrogen, oxygen, and the halogens. Now, some of the halogens do have access to d-orbitals, but hydrogen, oxygen, and nitrogen are primarily the bulk, along with carbon, that you're going to find in your organic molecules. All of those are found in quantum level 2, and they do not have access to d-orbitals. So there's no such thing as a 2d orbital. The earliest d orbital that you open up is a 3d orbital if you're in valence shell 3. So again, I don't want to say that you'll never have access to d orbitals in organic chemistry, but given the atoms that tend to be the focus in organic chemistry, it's very rare. And we're really focused on a lot of general chemistry and organic chemistry. We're not going to the super high advanced topics here. When we take a look at d-orbitals, the biggest thing you want to realize when you have hybrids that involve d's, so for instance sp3d or sp3d2, you can have things like that, is that they have the ability to violate the octet rule. Now when I say violate, they're not really violating anything in terms of forming a structure that they wouldn't be able to. The octet rule comes from the idea that you want 8 valence electrons based on the nice, neat Lewis structures you draw for those noble gases, because every atom should be aiming to have an electron configuration like a noble gas. Well, that's fine, but what we don't really show in Lewis structures is hybridization occurring. And when hybridization occurs, if you have access to d orbitals, you can distribute electrons into your sp-d hybrids, and you can form more than 4 bonds. And I'll explain that a little bit more when we get there. All right, and then finally, we're going to talk about orbital location and electron stability. Primarily what I'm referring to here is that s orbitals are going to have the greatest stability because they're the closest to the nucleus. That spherical structure hugs the nucleus, and then p and d and so on and so forth. We're getting further and further withdrawn from the area where the protons reside, so those electrons are not going to be quite as stable. They're going to be a little bit higher in energy, and they're also going to be a little bit easier to remove the further away we get. All right, so let's take a look as a refresher at some orbitals. Okay, and again, specifically because we're going to deal with a lot of the sp hybrids, I want to look at s and p orbitals here. So what I have up on the screen here are the general representations of an s orbital and a p orbital. These are not hybrids. These are your normal orbitals before any type of hybridization would occur. And we typically talk about these when we're talking about atoms because atoms will only undergo hybridization when they're getting ready to bond. So I wouldn't expect an oxygen or a nitrogen or a carbon in its regular atomic state to have any sort of hybridization going on. There's no reason for the orbitals to hybridize. Hybridization is a theory that helps us explain some of the geometry and bond length that we see when we start looking at covalent bonds forming and molecules forming. So the s orbital, again, is the one closest to the nucleus. And when we take a look at the s orbital, we can see the nice spherical nature that we have here. So we're talking about this guy right here. Now, as I mentioned in the overview, we have p-orbitals. The p-orbitals can take up multiple direction along the three-dimensional axes that they work with. And so we can have, think again about a graph. If I have the x and the y coordinates, you also have a z coordinate that is coming sort of through. Imagine if you take a two-dimensional sheet of paper in front of you, right? Running up and down is the y-axis. Running across, so side to side or horizontal, is the x-axis. And then there's another axis when you deal with three-dimensionality, which is directly through the sheet of the paper. And so through the sheet of the paper is the z-axis. It's that third dimension that we're giving here. And remember that when we deal with orbitals, they're three-dimensional. Even the s orbital is three-dimensional. It's a sphere. But the thing with the sphere is no matter how I turn it, I can't say, oh, well, now the sphere is in the x-axis, now it's in the y-axis, now it's in the z-axis. It just has its own axis. And so we only have the one s orbital, but we have the three p's because we can orient a barbell sideways or horizontally, up and down, which would be the y-axis, and then we could turn it towards us, and that would be the z-axis. So you will have px, py, and pz. And this is important to understand because this is why we can have an sp³ orbital or an sp² orbital. We have to be able to draw on more than one p orbital for our hybrid in order to create those types of more advanced hybridization orbitals. And so I do need access to 3 p orbitals in order for that hybridization to occur. Now, if you think about a hybrid, similar to something a lot of people refer to hybrid cars, that's an easy analogy because they're so common nowadays. But a hybrid is a mixture of 2 or more things, right? And the sum of the parts give you this new piece. So if I take a look at this, it's the merging of an s and a p orbital that's going to give me the hybrid orbital. So what happens is, if you take a look at the gray and the white portionalities, we have positive and negative lobes or portions associated with each of these given orbitals. Now what you'll notice about the s orbital, because it doesn't have what's called a node, which is this part right here, there are no electrons that are allowed to exist in a node. It's a separation. It gets into Schrodinger wave equations and theories about probability of where electrons can reside. That's a little more advanced than what we're going to go into right now. Okay, but what you want to realize is that an s orbital does not have a node. And so when we combine, we're going to combine the positive wave functions or portions of these orbitals together, and then we're going to look at the sum of the parts. And so what happens is, imagine that I combine the s and the p orbital together, and here we go. Here's our sp hybrid orbital. What you see is the 2 pluses came together. They formed a giant electron distribution, okay, or probability of distribution in that one lobe. And then we see the minus lobe, right, did not receive that same overlap. In fact, in comparison to the positive lobe, it has shrunk quite a bit. And so this is the process of hybridization. So many times students, when they see carbon and they sit through that first week of Organic Chemistry 1, and their professors turn around and they go, okay, here's the hybrid orbitals, right? I've had many students that come up to me and they say, oh, the balloons around carbon, right? And I'm saying, what do you mean the balloons? They're referring to the hybrid orbitals that the professor is drawing around carbon. Okay, so these balloons, as you would call them, are sp orbitals. Now that doesn't mean that it's sp hybridized, it just means that these are hybrid sp orbitals. So in this case, if carbon were to have all single bonds, we would be talking about something that's sp3. And again, I'll get into that in a minute. We'll show a little more detail and breakdown as to what's going on here. All right. Now, in order to explain the process of hybridization, I told you there were two things we want to take a look at, which is orbital overlap when we have incoming bonds. And then the other thing that we would like to take a look at is the general energy associated with it. So I'm going to clear the board here, and then we're going to do a couple of drawings to help us explain that. So let me clear the board and we will continue with that. Okay. So now that the board is clear, let's pick out some colors so that we can make this stand out a little bit. So what I will do, let's say that we have a carbon that's going to join to another carbon, and this will help you understand a little bit about what's going on with hybridization. Let's take a very simple molecule. We will take ethane. So CH3, CH3, ethane gas. When we take a look at ethane, we have to consider that the carbon-carbon bond is going to be the center here. All right, so if I'm dealing with a carbon like this, and it's got hydrogen, 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 and another carbon, the geometry of this would be tetrahedral. All right, now when we deal with tetrahedrals, we are going to be dealing with sp3. It's involving all single bonds, okay, which are also referred to as sigma bonds, which has this sort of, it's not a 6, okay, it's the sigma, the Greek letter for sigma, all right? Sigma bonds, whenever you have the 4 sigma bonds and no double bonds or triple bonds present, it's a tetrahedral type of geometry, and tetrahedral geometries take up sp3 hybridization, and we'll show you why. So, what I want you to think about right now, if we have sp3 hybridization, it means that if I were to draw these orbitals, every single sigma bond is coming from an sp3 hybridized orbital. So in other words, all of these sigma bonds are dealing with sp orbitals. Okay, so sigma bonds exist in hybrid orbitals. Okay, in comparison to pi bonds, which are going to exist in p orbitals, and we'll take a look at that when we talk about sp2. So here's the carbon for my CH3. It's going to be bonded to another carbon. Okay? So the idea here is these carbons are going to need to overlap, because what they want to do is share these electrons. So here, when they share these electrons, this is going to be a sigma bond. Specifically, it's going to be the sigma bond that I've pointed to right here. Okay? So this sharing right here, this overlap, is essential in order to create a good carbon-carbon bond. And so when I'm looking at this, the sp3, remember when we had that previous structure up, the balloon had gotten larger, right? The hybrid orbital made a much larger area for electrons to overlap in. And so the idea here is that we want to attempt to take these two large areas where we can overlap electrons, and we want to bring them together so we have the maximum ability to bond these electrons together and create these covalent bonds. All right, so this can be a little bit difficult if you are only working with p orbitals, or even more so if you're looking to combine an s and a p orbital without hybridizing them, because they have very different geometries. Okay. Now, one of the other things I wanted to point out here is that we have some hydrogens present. And when we have hydrogens present, let's pick out a different color. We'll do blue. Okay. So when we have hydrogens present, the hydrogens are not going to have any type of hybrid orbital, and that's because hydrogens don't have p orbitals. If you think about a hydrogen has a 1s orbital. That's it. There's no such thing as a 1p, and they exist in the first quantum level. They have 1s, whereas carbon, right, would have 2s and 2p. So it has the ability to form hybrids. You can't form hybrids with just an s orbital. It wouldn't work, because the definition of a hybrid is we need 2 or more different types of orbitals to combine. So these nice bulky balloon-like hybrid orbitals are still going to be beneficial for overlapping with the s orbital. So here come the hydrogens. They are all going to form S overlaps with the sp from the carbons. And that will give you these hydrogens here that are bonded to their respective carbons. And so the overall molecule, the carbons, would be referred to as sp³ hybridized, whereas the hydrogens would just be S. They wouldn't even be S hybridized because, again, S is not a hybrid. So that is a general look at the overlap that we're talking about here. Now, this still confuses some students, and one of the things that I use to point out and sort of help with this is I want you to think about the general structure or the electron orbital diagram for carbon. And this can help you understand this. If I take a look at carbon, and we just mentioned it has 2s and 2p, here's carbon. So 2s, 2p, it certainly has 1s, which is full as well, but again, we're only dealing with the valence. So carbon, having 4 valence electrons, we follow Hund's rule, meaning we fill each of these with 1 before we would fill another, and we also have to fill from lowest energy to highest energy. So here's our carbon. Okay, so I tell students, think about methane. They've shown that methane, when you look at its structure, all of these bonds are equal to one another. So none of them are longer or shorter than the other. If I were to look at, here's hydrogen, right? Hydrogen only has a 1s, and it would have 1 electron in that 1s. So if I think of carbon, and I was looking at the electrons that are going to bond with the hydrogen, I would have a carbon. Let's say that this electron is found in the 2s. This electron is found in the 2s. Right? And then I have 2 electrons that are found in the 2p. Right? So here's one, and here's another. If this is the case, I'm going to have an s orbital from hydrogen overlapping with an s orbital from carbon. Then I'm going to have another hydrogen with an s orbital overlapping with another s orbital from carbon. But then look at these. I'll change the color here. Okay? If you come down and you take a look here, I'm now going to have a hydrogen overlapping with a p orbital from carbon for these two. And what this would lead to is a carbon that's going to have 2 hydrogen bonds that are shorter, and then 2 hydrogen bonds that would be longer, like this. So these would be involved in the P, whereas these would be involved from the S. But when we've done studies, when chemists have done studies, they've shown that this is the structure. They're all equal. Every carbon-hydrogen bond is equal in length when we're dealing with methane. And so we know that something has to be going on because we do not see this type of structure where 2 of the hydrogen carbon bonds are elongated and have a greater length because of the p-orbitals that are further away, and then 2 of them that are s overlapping with s. We see somewhere in between. So what we say is, well, these are not as short as the s-s overlaps, but they're also not as long as the sp overlaps that we would have seen here. And so there must be something that's coming along to hybridize or to make all of these equal when we blend them together, because we see what comes out in methane are 4 equal bonds. They're of equal energy, they're of equal length, and so we have to explain that somehow. That's where hybridization and valence theory comes in. All right, now in terms of, I'm going to redraw this carbon diagram because this is important to understand. So that's overlap. The other thing we discussed was energy, and we want to bring up energy here. So with energy, and this is going to start leading into the concept of sp³ hybrids, because I'm going to show you an sp³ hybrid in this example. Again, take carbon. Carbon has 2s, right? We put these electrons in here, and then carbon also has 2p. So what's important to think about here is when I go along this axis, this is energy, and the energy is increasing as I go along. So that is to say the electrons that reside in the 2p orbital are going to be higher in energy than those found in the 2s orbital. And that has to do with proximity to the nucleus. Again, tying this all back together, s orbitals are tighter in terms of their hug of the nucleus, which is where the protons are, and the protons are the stabilizing force for the electrons. So the further my orbitals get from the nucleus, the higher in energy they're going to be. And so when I take a look at this, what's really happening is that carbon gets ready to bond, and it says, okay, what I'm going to do, I'm going to bring the electrons and the s orbital and the electrons from the p orbitals, and we're going to meet somewhere in the middle ground. And so what I'll do is I'll bring in all 3 p orbitals. So I'm going to do all 3p, okay, and I'll bring in my 1s. So that gives me a total, orbitals in is going to be orbitals out. That gives me a total of 4 orbitals because I put 3 p orbitals in and my 1s. Now when I say 1s, I'm not referring to the 1s level, which is down here. I'm saying I've brought in 1s orbital. Specifically, it's the 2s level. That's the orbital I'm bringing in. So what happens? Again, if I'm counting here, and I'm going to bring this in color so everybody can see it here. Okay. If I bring in 1, 2, 3, 4 orbitals total, then I'm going to have 1, 2, 3, 4 orbitals out. Okay, think about it just like if you were putting it in a blender, right? The ingredients I put in, I may mix them and they may become something that's different or a hybrid mixture of the original elements I put in, but I should still be getting the same amount out, right? If I put in 1 cup of flour and 3 eggs, by the time I mush it all up, I still have 1 cup of flour and 3 eggs. It's a different consistency. They've now blended together. They've given me some sort of a hybrid mixture, but items in, items out. So that's where we get this, all right? Now, if you remember, I just mentioned Hund's rule a minute ago, and that's important because Hund's rule states that when we're dealing with electrons that are of equal energy levels, the fancy word for that is degenerate energy levels, okay, degenerate orbitals, we put 1 per orbital before pairing. And that's because there's some slight repulsion between paired electrons, and so it's better for them each to have their own spot if it's at the same energy level before I start pairing them up together. All right, so what I've got here are 4 electrons. Now, where did I get 4 electrons from? I couldn't just throw in 4 random electrons unless they came from somewhere, and they came from right here. Here's 1, here's 2, here's 3, and here's 4. So it's not the fact that I have 4 orbitals over there, right? Because this one was empty. This one didn't have an electron in it. It's the fact that there were 4 electrons to start with, and I now have 4 open slots. Keep in mind that I now also no longer have the 2s residing here or any of the 2p's. So they were all used up in the hybridization process. I brought all of them into this process in order to create these orbitals. So these are the only orbitals that now are available for electron deposit. So I have to put 1 in each one, okay? And again, the reason that this is referred to as sp3, because a lot of students say, isn't it sp4 because you have 4 of these sp orbitals? No, it's sp3 because this is the number of p orbitals that were brought into the hybridization process. That's where the 3 is coming from. The 3 doesn't deal with the number of electrons. The 3 does not deal with the total number of hybrid orbitals. The 3 deals with the number of p orbitals brought into the hybridization process. Okay? So that will help to show you that these new hybrid orbitals are at a lower energy level than the p orbitals. They're at a higher energy level than the s orbitals. So take a look at this. Here's where I would place sp if I were to place those types of hybrid orbitals. The s is lower in energy, the p is higher in energy. But what I'm doing here, the exchange, is that I'm taking 1 orbital up to a higher energy level, but I'm bringing 3 orbitals down to a lower energy level. So this is a beneficial process in terms of the energy that's going to be involved or associated with the orbitals and their corresponding electrons when we get ready to bond. So hopefully this explains what we're talking about when we say sp3 hybridized. Now, each of these, think about carbon here, each of these electrons are associated with one of carbon's single bonds. So here's my 4 unpaired electrons, right? And if I take a look at this, we were using the example of methane. If methane has the 4 single bonds, carbon's donation here was 1 electron each from the hybrid orbitals. 1, 2, 3, 4. And then, of course, hydrogen would need to bring its own corresponding electron in order for the covalent bond to occur and that sharing of electron to occur. All right, so that's sp3, again, associated with tetrahedral geometry, and it's associated with all sigma bonds. When we're dealing with nothing but sigma bonds around the center carbon or center molecule, you're going to be dealing with these hybrids. So now let's go ahead and take a somewhat similar look at sp². Now sp² is going to be involving how many p orbitals? What would you think? Based on the name, sp² is going to involve 2 p orbitals being brought in and then one of them, whoops, being left behind. Switch to the pen. I'm going to stick with carbon because organic chemistry does tend to come up a lot on the MCAT, and it's one of the easiest examples to work with. We've already started with that, so let's stay on that path as we explain hybridization. But I want you to realize I could talk about the same thing with oxygen, with nitrogen, with any of these other elements that are in group 2, and I would be able to talk about their hybridization in the same general sense. All right? So if I take a look here at carbon, carbon is 2s and 2p. So let's redraw our structure here, our energy. Okay, and then I'm going to do the energy axis going up along here. Right? So now, if I'm going to deal with something that is sp², it should have 2 p orbitals. That's the correct answer. 2 p orbitals should be brought into the hybridization process, which means 1 p orbital will be left behind. And that p orbital that's left behind is going to be important because it will be what is responsible for hosting pi electrons or pi bonds. Sigma bonds are not associated with p orbitals. They are found in hybrid orbitals. So I would do the same sort of process where I'm going to say, okay, let me bring this together, but now I'm only going to be involved with 3 because I'm going to get the S being donated. The S always has to be donated in order to make a hybrid with p orbitals. But then I only need 2 of my p's. I'll keep the third one behind because I don't really need it right now. So what I'm going to do then is I'm going to say, okay, so here are my sp² hybrid orbitals, and I can fill 1 electron in each in order to form my sigma bonds, right? So let's take a look at an example where this would be the case. And a simple example to use here would be formaldehyde. So you've got the carbon in the middle, you've got the hydrogens, again sticking along with the carbon-hydrogen overlap sort of idea. But now we have the carbon-oxygen, okay, and this involves a set of pi electrons. So this carbon here is going to be sp² hybridized. And when we take a look at that, that makes sense because if I look at the number of sigma bonds involved in this carbon, there are 3. I have 1 to the oxygen, 1 to the hydrogen, another 1 to the hydrogen, right? So those are the sigma bonds. Now let's change color here because the remaining one is going to be the pi bond. So this right here is going to be associated with the pi electrons, right? So that means that I'm going to, once I redistribute here, I'm still going to have a p orbital left, and that p orbital is going to have my 4th electron, right? Whereas the sp²s would have the other 3. So take a look at this. We need to do a little bookkeeping to make sure that this all makes sense here. All right, I brought in 1 s and 2 p orbitals. 3 orbitals in, 3 orbitals out. I have 3 orbitals here associated with my sp² hybrid orbitals, right? And then I say, okay, well that left one p behind. So if I distribute 3 of my 4 electrons to the sp2s, then that leaves 1 electron behind that can go into the p orbital, and that will be involved in the pi bond. Okay, so the corresponding bonding partners here are going to be, right, so how do I want to do this? Let's show this in, again, more colors. The colors are helpful. So we're going to say that the hydrogens, let's circle them in this blue color, right? Here are the hydrogens. They are going to offer up 2 electrons. This is if I start bonding now, okay? And then the oxygen, let's give the oxygen a different color. The oxygen is going to offer up, 1 for the hybrid, and the other electron it offers up, it's going to keep in a p orbital as well. So double bonds occur when p orbitals overlap. So carbon is going to have a p orbital associated with it. And then oxygen will also have a p orbital associated with it, right? So let's go back to the colors we were using here, right? The hybrid orbital right here is going to be different than the p orbitals. So this is going to be the sigma bond that is shared between the carbon and the oxygen. So this is one of our bonds, right? The carbon-oxygen bond. There's another carbon-oxygen bond, the pi bond. We showed that one in red. So let's pick out red here. Okay, and these electrons exist from the p orbital overlap. So here's an electron here, here's one here. This is where the pi bond comes. And the pi bond really will occupy space above and below the sigma bond like this in these p orbitals. So a lot of times in books, students get confused because they show something that looks like this. A lot of my students will call it the hamburger, right? So they'll show this, and then they'll show this. And they'll say pi, sigma, pi. And what they're really showing is that the sigma bond, okay, here's atom 1 and here's atom 2. What they're showing is that the sigma bond is sort of this middle link here, and then the pi electrons are going to be placed above and below. And a lot of students say, well, isn't that a triple bond? No, because electrons are always in movement, right? They're not static. They don't stay where they are originally drawn. That's not where they're located. They're moving about. And so the 2 electrons that make up the pi bond, they orbit, or they basically distribute themselves around that sigma bond. They sort of overlap it in the p orbitals that are found further away from the hybrids. And that is what's happening when we've got sp2, okay, and we have these double bonds or these pi bonds. Now keep in mind that when we deal with single bonds are considered to be the longest bonds, and then pi bonds, as you layer, so you get a double bond is shorter, and then a triple bond, the triple bond is even shorter when we're dealing with that. So you have to think about the fact that these, again, they're not static bonds. They don't just stay linked where they are. They occupy some amount of space where they're constantly going to be in rotation as we're dealing with them. Okay, and so the pi bonds exist, or the pi electrons that make up the pi bond exist above and below this general area. They exist in the p orbitals. So you need p orbital overlap in order to have pi bonds. That's very important. You have to have p orbital overlap in order to have pi bonds. And that means I can only have pi bonds if I have p orbitals in the first place. So anything with a pi bond must have some amount of p orbital character left behind. Whether it's sp2, whether it's sp, sp3s should not be hosting any type of pi bonds because we don't have p orbital overlap available. All right, so that helps to explain sp2. Let's clear the board once more. We'll talk about sp. I'm going to go a little bit quicker as I start talking about sp, simply because we've already looked at sp3 and sp2 in some detail. You should be knowing what to expect by this point as we sort of round the corner to sp. All right, so let's take a look here. sp, sticking with carbon, okay, carbon, if we draw the energy diagram, we've got 2s, we've got 2p, and we take a look at the electrons here, right? And so if I'm going to do the hybridization, in this case I bring one s and one p into the process, and that gives me sp hybridized. And so I only need 2 electrons here, in which case that means there are p orbitals left behind, and the p orbitals that are left behind would be 2. So I've got an electron that's here, and I've got an electron that's here. These are the p, okay, and switching back to the black just so we can label it, these are the hybrid orbitals that are down here. Notice the hybrids are always below the p in terms of the energy, because one of the things we talked about at the beginning is that the hybrid, or the process of hybridization is beneficial in terms of lowering the energy of these electrons that are getting involved in bonds. Remember, the other part is good orbital overlap, especially for those sigma bonds that are forming. So when we take a look here at sp hybrids, you're talking about something like acetylene. That's the torch fuel. You have carbon, hydrogen, and hydrogen. So you've got this triple bond here. What's occurring is, if I look at this location, I've got 1 sigma and I've got 2 pi bonds instead of 1 pi bond. And then here, these are just sigmas, right? So take a look at each carbon, because this is a diagram for 1 carbon. If I look at each carbon here, each carbon would be involved in 2 sigma bonds. One of them would be the sigma between the hydrogen and the carbon. The other would be the sigma found between the carbon and the carbon. So what does this look like? Let's draw it in a different color. All right, so the hybrid, we'll use that teal color. So I'm marking my board up. All right, so here we go. Carbon, right? Here's one of the hybrids. Here's the other. Okay, and then here's the overlap from the other carbon. Carbon. Okay. So there are the hybrids. This guy right here, this overlap, is going to be the sigma bond. And then this one right here, right, is going to be the other sigma bond for the hydrogens. So what's going to be present here is we need to deal with the p orbitals. So we're going to have a p orbital this way, right? So that's where one of our double bonds would exist. And then we would also have, this is going to be a little messy to draw, we're going to have a p orbital, because I haven't drawn the z-axis p orbitals yet. We're going to have p orbitals coming out this way. And so let me draw this in a separate color. These are going to be the pi electrons. We'll draw them in orange. Okay. So I've got pi electrons here. Okay. That's one group. And then I'm going to draw the other set in a different color so you can see where they exist. So we'll do purple. Okay. So the other is coming around back here, and then is also coming around the front here. Okay? So those are the pi electrons that we have in the p orbitals. But notice I need 2 sets of p orbitals for a triple bond. So that teal color, I lay the foundation, I get my sigma bond going, then I require 1 p orbital to bring in 1 set of pi electrons. Now I've got a double bond. I require another p orbital to bring in a second set of pi electrons, and that now becomes a triple bond. Remember, and I should mention this, I don't know if I mentioned it for the sp². sp² is trigonal planar, it's flat, right? And it does deal with pi electrons. And then sp is linear. So when we look at acetylene, the structure, it would just form a straight line, a 180-degree bond angle. And what we would have there is the triple bond, meaning 2 sets of pi electrons, and then we would also have the sigmas that underlie that for the hydrogens. and for the carbons that are there. So that explains sp hybridization and the linear. All right, so let's go back up and take a look at this list here. We've now covered and hopefully should understand the general theory of hybridization and what's going on, orbital overlap and the energy bonding. We've talked about sp3, sp2, and linear with the sp hybrids. We understand pi electrons and that they must occupy p orbitals in order to form those pi bonds. So let's talk about the cheat method real quick here, and then I will briefly talk about d-orbitals and some of the effects you would see with that, and then we'll again go over or recap orbital location and electron stability. We've kind of been talking about that along the way, and then we'll do our normal questions. We'll wrap up with a summary, and we'll be good to go. All right, so let me clear the board, and I'm going to talk about the electron domain rule really quick. So give me a second to clear that, and then we'll get started. All right, so now I have this up here. This is the brief cheat rule, okay, that's going to help you if you get stuck in a situation. So what you need to do is you need to count the electron domain that are found around the center atom. So what is an electron domain? An electron domain is considered to be any lone pair and any bond of any type is one electron domain. So a single, a double, or a triple is going to be one electron domain. So don't get confused, because I teach this to a lot of students and they'll say, oh, a triple bond, that's 3 electron domains. No, it's 1. The triple bond occupies one space around the central atom or atoms if you're dealing with, you know, something like acetylene, like that molecule we were looking at. So let's stick to the molecules we were using as examples because they'll make sense to us. So here is methane. Here is the formaldehyde, and then here's the acetylene. All right, so if I want to find out the hybridization of a specific atom, when we say specific here, I'm talking about the carbons in the center. Okay, this carbon, and we could also look at this carbon, and I'll tell you what, we're also going to look at the oxygen here too, once we're done with the carbons, because that'll be useful, and then I'll give you another molecule to work with. So what you want to do here, any lone pair or any bond, you're going to count it up, and then you're going to use n-1 for the sp value. So this will work as long as you don't have d-orbitals. If you have d-orbitals, you could figure your way around it, but you have to realize you cap yourself off at 3 for the p. So then you'd have to, if you had a number that was larger than 3, you'd need to start heading over to d-orbitals and, you know, do sp3d or sp3d2, so on and so forth. So if we take a look at this here, this carbon has a single bond, that's 1 electron domain, a single bond, 2, 3, 4. So there are 4 electron domains. 4 minus 1 is equal to 3. So this must be sp3 hybridized. Okay, simple as that. Now again, n, we should state here, let's clarify, n is equal to the number of electron domains, right? Electron domains. So if I take a look at this carbon has 1 single bond, 2, there's a single bond, and then 3, here's a double bond. Remember, the double bond will only be counted as 1 electron domain. So 3 minus 1 equals 2. That means sp2 for the hybridization. Okay? And then if I come here and I look at this, I say, okay, well, I now have 1 electron domain, the single bond, 2 electron domains, the triple bond. And it's the same for both carbons. If you look at them, they're identical. So what I have here is 2 minus 1. That's equal to 1. We tend not to say sp1 because it's redundant. The p already represents 1 of itself. So it's just sp hybridized if I have the 1. So I hope that that makes sense, and I also hope that you can appreciate and understand why I didn't jump to this right away, because you will have questions that can come up on the MCAT that are theory-based, and they'll say, you know, something about p orbitals and pi electrons. And if all I did was I jumped in and I said, hey, look, you can solve for hybridization using this cheat method. Aren't you happy? That's all you need to know. 5-minute video, we're done. That's not going to help you. It may on certain questions where it says, you know, the carbon in molecule X is considered what type of hybridization, and you could answer that, given this technique here. However, if they were to ask something about how many p-orbitals were involved in, these pi electrons, or they were asking you where pi electrons would have to reside, you need to understand the theory of hybridization. They could also ask a question about why hybridization is occurring in the first place. Knowing this isn't going to tell you anything about that. So I hope you can appreciate the theory that goes behind all of this and why we took the time to understand this material before I jump to the cheat method. Because usually when I show this, students just get so excited and they say, well, why didn't you say that in the first place? Why did we spend an hour and a half talking about all of this detail and now you're bringing this up now? And I say because you don't want, cheat methods are great and you should utilize them when they can be applied. But you don't want to constantly rely only on those, because then you hit a wall when you have to answer deeper questions or theory questions. You want to understand the whole scope, and then at the end you pick up the cheat method, tuck it in your pocket so you have it as an ace up your sleeve. If you come to a question you can save some time on. Okay, so hopefully that makes sense. Now I do want to bring up one other example here, as I mentioned. And the oxygen, before we forget, the oxygen, right? So the oxygen here, if I were to take a look at this, how many electron domains are around the oxygen? Well, I've got a lone pair, that's 1. I've got another lone pair, that's 2. And then the oxygen is involved in the triple bond, so that's 3. So 3 minus 1 is 2, so this oxygen would also be sp², right? So we could say that this carbon-oxygen bond is an sp² bond, because they're both sp² hybridized. All right, so I was about to delete it there. I forgot about the oxygen, and I reminded myself because I'm going to give you another example involving oxygen. Okay, so let's take a look at water, right? So if I take a look at water, very common molecule, especially in biochemistry and organic chemistry for that matter, right? I've got these lone pairs, 1, 2, 3, 4. So based on that, what would the hybridization of water be? Well, you could go through and you could look at the proper geometry. The proper geometry here would be tetrahedral. It's a subclass of tetrahedral called bent, and that's because there's only 2 bonds, and then the 2 electrons are repulsing one another. They're pushing those bonds down, right? And when I look at that, okay, I then say, all right, well, if I have 4 electron domains minus 1, that's 3. So it turns out that water is tetrahedral, it's sp³ hybridized. That's also important that I just said tetrahedral, because a lot of students will typically associate or memorize that when you deal with one specific geometry, it associates itself with one type of hybridization. And that's true. You can say, this is tetrahedral, so it's sp³. This is trigonal planar, so it's sp². This is linear, so it's sp. You could do that. But again, you're going to handicap yourself if you don't understand the theory underlying that. You're simply making a connection and memorizing 2 + 2 is 4 sort of thing. You need to understand a little bit deeper in terms of the theory of hybridization here, which is why we spent the time to do this. All right? So that's the quick cheat rule there for the electron domains. The one thing I wanted to bring up here for d-orbitals, because that was the next thing on our list. When you're dealing with something that has d-orbitals, or at least access to d-orbitals, you can hybridize beyond the p level. So in other words, if I have sulfur, sulfur is a common example. Okay. Let me bring up my pen here. Okay, so if I have sulfur, sulfur has a 3s. It has a 3p, but sulfur also has a 3d. Now the 3d level in sulfur is empty, and there would be 5 of these here. The p is only going to have 3, the s is going to have 1. All right? But what I hope you can see here is that if we choose to do a hybridization process, okay, I can get more than 4 orbitals that I bring over here, right? I can do 1, I can do 2, I can do 3, I can do 4, and that's where I capped myself when I had only S and P available. So things like carbon, oxygen, nitrogen, right? All of these would only have the S and the P available. But what happens when I get to something like sulfur, something like phosphorus? Well, it's got a 3D shell because it's in level 3. The 3D shell is currently empty. There's no electrons in it. So if I were to consider the S, I would say here's 1 electron, 2, 3, 4, 5, 6. Because I would have 6 valence electrons. Sulfur normally has 1, 2, 3, 4, 5, 6 valence electrons, right? However, I could take each of these electrons and put them all into a hybrid orbital if I so desired. So in other words, I could say I have 6 electrons. I'd like to make 6 hybrid orbitals for those electrons. What I have to do is tap into some of the D in order to do that. So now I'm going to bring in an s orbital. I'm going to bring in 3 p orbitals, and I'm going to bring in 2 d orbitals. So I tally that up. Here's 1 plus 3 plus 2. That's equal to 6. So I have room for all 6 electrons now to be placed into the hybrids. Okay, and so this is why you can see something like a sulfur that's got 6 bonds associated with it. So we would call this octahedral geometry. This gets again into some of the more inorganic type material, but what you want to understand here is why sulfur is able to form more than the 4 typical bonds or the sp3. Why can it go above that? It can go above that because it has access to the d orbitals. That's why it's able to do that. And so I can have something where, let's say, I've got fluorines around here, right? Sulfur hexafluoride. I can have a molecule like this. This does not violate any sort of valence rules for sulfur. For carbon, this would not be appropriate because carbon cannot have 6 sigma bonds. It only has available the 4 because of its P. So anytime you see these bonds, okay, for instance, another example here would be you can have H2SO4. And the structure of H2SO4 looks like this, right? Well, if I take a look here, I've got sigma bond, a sigma bond, a sigma bond, a sigma bond, and then I have 2 pi bonds on top of that, right? So if I look at that, if I were to try to do that with a carbon, I would say, okay, the carbon can do the 4 sigma bonds, but there's no p orbitals left in order to form those double bonds or those pi bonds, right? The sulfur has the ability to do that. It can leave some p or some d behind in order to tap into that and create the 4 sigma bonds and then layer the pi bonds on top of it. All right, so that's really the extent to which I'm going to cover dehybridization. But if you understand the premise of S and P hybridization in detail, all you need to know is that once I have an element that has access to d orbitals, the hybridization process can continue from there. Now, again, hybrid orbitals will only contain single bonds, so I would not, unless it's a lone pair, start forming pi bonds in here. Okay? You can have lone pairs that exist in hybrid orbitals, but you're not going to have pi bonds. So when you deal with this, you typically are not going to start extending or creating more hybrids than necessary. So in other words, if I only have 6 electrons in sulfur, there's no need for more than 6 hybrid orbitals. It wouldn't make sense for me to bring in the additional 3 Ds that were left behind because sulfur can't utilize it at that point. They just sit around as empty d orbitals. They aren't brought into the hybridization process if there's no bonding going on. All right? So that takes care of the d orbitals. The last thing before I bring up the questions here that I just wanted to mention one more time is the location of the orbitals relative to the nucleus and their stability. So this can be shown through these energy diagrams that we've been doing. So we've sort of been talking about it along the way, right? And then I have 3s here, and then I have 3p. And then technically, I'm not going to show it here, but you do fill up 4s before you deal with 3d. Okay, but I'm just going to put 3d there for right now. So you've got your s, you've got your p, and you've got your d's, right? So, and we can also, for the sake of it, put in 1s down here. So this is the energy going along this way. So why do we see the energy trend that we do here as we're dealing with the hybrids and the various orbitals? Well, here's the nucleus, right? That's the stable portion with the protons. The first thing is the 1s shell. It's the closest to the nucleus. Then we have the 2s shell. That's the next closest, spherically speaking, to the nucleus. It grips onto that. Then we would have the 2p's. They start to elongate themselves further away from the nucleus. So the electrons in these would reside in these outer areas here, right? And then, as you open up a new quantum level, here's the 3s shell. Okay, that gets further. And then we have the 3p shell. So I think you can see where I'm starting to go with this. Let's bring this down here. We're getting further and further out from the nucleus. Every time we do an S, a P, a D, etc. So the D's are going to be even further out than the P would be. And as you start to do this, you're getting further and further away from this center spot. And this center spot is where the protons are. Okay? So the more S character you have in your hybridization, all right, the more stable the electrons are going to be in terms of that hybrid orbital. So in other words, if I have something that's sp in nature, that means it is 50% S in character, and it is 50% P in character if I'm looking at an sp hybrid. And an sp hybrid has a good bulk of S character, so that means any electrons that are found involved there are very close to the nucleus. And we said that the triple bonds or the shortest bonds, they're brought in, the electrons are brought in closer to the nucleus, or the nuclei if you're talking about sharing the electrons. Right? So if I have something, let's say like sp3, something that's sp3 is only going to be 25% S makeup in its character, and it's going to be 75% P makeup in its character. So if I find electrons in sp3 orbitals, those electrons are going to be further removed from the S characteristic and therefore further removed from the nucleus due to the shape of the orbital, because it's more P-like in nature than it is S-like in nature. Because of that, that means the sigma bonds, the single bonds found in those sp3 types, are going to end up being a little more elongated. They're going to be not as stable as the ones drawn in close to the sp. All right? So orbital location is important for electron stability when you're talking about that. Overall, hybridization is a beneficial process when we get ready for bonding. Orbital overlap is improved, and we see an improvement in the energy of the electrons in terms of the diagram. All right, so that wraps up the general portion that we're going to do here. I will bring up some questions, and then we will do our summary as usual. So let me clear the board to bring these questions up, and then I will go over them and give you guys a chance to work on them. All right, so here are the questions, or at least the first set of questions that we're going to go over in relation to hybridization. I will bring up a few more after this. So number one, which of the following molecules is best described as sp hybridized? So when you're doing this, you're going to want to take a look at the Lewis structures involved for each of these and determine the central atom, which one is going to best be categorized as sp hybridized. You have several choices there. Number two, the orbital hybridization is thought to occur due to, so we're saying any general hybridization of orbitals is thought to occur due to what? And you've got several different options here. So that's more of a theory question to see if you understand why hybridization is actually occurring. And then number three, we have an organic mechanism down here. The mechanism below shows a nucleophilic attack. What is the hybridization of the atom that is accepting the nucleophile? Okay, so remember, nucleophiles are electron-dense particles or compounds that are going to attack an electrophile or an electron pore area. So this particular reaction has an electrophile, and what it's asking is, what is the hybridization of the electrophile in this reaction? So go ahead and pause the video, work on these as you normally would, and then we will take a look at them together. So I encourage everybody to try this before I do the walkthrough, and I'll see you all in just a minute. Okay, so hopefully everybody had a chance to work on these, And what we're going to do now is walk through each of the individual questions. So number one, which of the following molecules is best described as sp hybridized? So if you take a look here, some of these you may have been able to eliminate right off the bat. I would hope that the easiest one, especially after this lecture, would be that you got rid of methane, because methane is a carbon with 4 bonds to hydrogen. We used it quite often in our examples, and this would be something that is sp³ hybridized. We would not have sp hybridization here. So that leaves the others. NH3, if you were to draw the Lewis structure, would have a lone pair of electrons, and it would then have the 3 hydrogens associated with it. Turns out that this is also sp³ hybridized, and you could have used the n-1 rule if you were struggling with this, saying here's 1, 2, 3, 4 electron domains, and so it would be sp³ hybridized, so that is out. Okay, and then CO2, if we take a look at that, the structure of CO2 is a carbon double bonded to an oxygen with its lone pairs, and the same thing on the other side, carbon bonded to an oxygen with its lone pairs. Turns out that this is sp hybridized. You could have used the electron domains and counted here's a double bond and here's a double bond. You could have also said this is linear, and linear is going to result in sp hybridization. And you also could have dug deeper into the theory and said, well, this carbon is resulting in 2 pi bonds. It's 1 pi bond on each side, so there's 1 pi bond on this side, 1 pi bond on this side. However, if we require 2 pi bonds, it means we're going to need 2 p-orbitals. And if we need 2 p-orbitals, we can only recruit 1 p-orbital into the hybridization, making it sp. So this is the correct answer. And if you were to draw out the boron trihydride, you would see that this is trigonal planar with your single bonds, because boron has the following Lewis dot structure with 3 unpaired electrons like this. You can form 3 bonds. This is trigonal planar. sp² would be the answer for D. So carbon dioxide is the correct answer for sp hybridization in this grouping. Number 2, orbital hybridization is thought to occur due to, and we have several options here, better orbital overlap during the bonding process. Well, that's true, so we can already select that. Let's take a look at the others just to see. Higher energy levels of the hybrid orbitals. Well, that's incorrect. That's not one of the reasons that we promote this. The higher energy levels of hybrid orbitals, the orbitals are actually going to be lower in energy than those p orbitals. So hybridization will lower energy, and that's a beneficial process. But higher, that's not the case. The ability to form pi bonds between atoms. Well, again, you have to be careful what you're looking at here. If we're forming pi bonds between atoms, hybridization doesn't really play any role in that. It's the p orbitals that are responsible for any sort of pi electron activity when we're forming double and triple bonds. And then finally D, tetrahedral structures having sp³ hybridization. Well, this is sort of just a statement. Tetrahedral structures have sp³ hybridization, but that's not why orbital hybridization is thought to occur in the first place. So the correct answer here would only be A. Okay? And better overlap of orbitals during bonding is very important. However, you could also, it wasn't present here, but you could also say that lower energy levels of the resulting hybrid orbitals is another beneficial effect and one of the reasons hybridization would occur. But the orbital overlap, that's the primary one, and that's also the one that would be best suited for this particular question. All right, number 3, show the mechanism below shows a nucleophilic attack. What is the hybridization of the atom accepting the nucleophile? So if we take a look here, all right, this reaction right here, this is the nucleophile. It's a Grignard reagent, and it's this ethyl group, it's CH3CH2, that is the nucleophilic part. This CH2 has a partial negative charge associated with it. I put a lone pair there. Some people tend to show this as a minus with the separation between the magnesium bromide. Technically, it's a very large partial negative. Okay, so when this attacks, the important part for this question is this is the nucleophile. So this carbon right here is accepting the incoming nucleophilic attack. And this carbon, if we take a look at it, it's involved in a carbonyl, it's a ketone setup. It's got alkyl groups on both sides. This right here is going to be sp² hybridized. So if you look at your options, C would be the correct answer here. All of the others would not be present. And you especially should have avoided answer A, because the carbonyl, if we're dealing with a carbon, or if you were looking at oxygen or anything else for that matter, all the atoms involved in this particular setup, in this group over here on the left, they are all found in group 1 or 2. In terms of their quantum number, so they don't even have access to d-orbitals. So A is definitely out right away. You should not have even considered A. And then you go through B, C, and D, and you would have to come to the correct conclusion that it was an sp² hybridization there. All right, so that is the first set of questions. Let me clear the board. I'll bring up a couple more here, and we'll work on those, and then we'll do a nice summary. Okay, so here's the other set of questions. I'm going to keep it to 2 more because we still have to do the summary and I don't want this video to get much longer. So number 4, sulfur has the ability to form more than 4 bonds. This is most easily explained by the fact that, and you have choices there. And number 5, hydrogen is one of the few elements that lacks the ability to hybridize. So why is this? And you have several options there. So pause this, try to work on these, and then we will go over the answers in a minute. Alright, so number 4, sulfur has the ability to form more than 4 bonds. This is most easily explained by the fact that, so let's take a look at the options here and see which one fits best. Sulfur has 6 valence electrons, allowing up to 6 bonds. Now while there's some truth in this, it does have up to 6 valence electrons, and you're going to need electrons for each of the bonds you'd like to form. That isn't the true reason that it can form more than 4 bonds. And to prove that to you, if we take something in its class, meaning the group that we find it in, we can go right above sulfur and we would find oxygen. Now oxygen has 6 valence electrons. However, oxygen is only able to form 4 bonds, despite the fact that it has 6 valence electrons. So this would not be appropriate reasoning. It's kind of a fact that also helps to support this, the fact that if I'd like to form 6 bonds, I will need at least 6 electrons, but that's not the main reason driving why I can form more than 4 bonds. Case in point, if I give my oxygen here the bonding ability and it has 6 valence electrons, it can still only produce 4 bonds max. So this is out. This is not the best answer here. The lone pairs on sulfur are nucleophilic. Well, that is true. So when we have lone pairs of electrons, they act nucleophilic, and sulfur would have 2 pairs. However, that doesn't explain why it can form 6 bonds at one time, or 5 bonds, or more than 4. All that explains is that sulfur can potentially be nucleophilic because it has a lone pair, so that's out. Sulfur has d-orbitals that it can hybridize. This is a very good option because d-orbitals that can be hybridized means that I can start creating multiple hybrid orbitals that electrons can reside in. So in other words, when I have sp3, that's an s, 1 s, and 3 p's. That's a total of 4 valence shell, or I'm sorry, that's a total of 4 hybrid shells that contain electrons. I need d in order to start going beyond that. So if I brought in 1d to the hybridization process, I'd have a total of 5. If I brought in 2d, then I would have a total of 6. And so this is the best explanation here. The fact that there are d orbitals in the 3rd quantum level and above means that the sulfur can start hybridizing more than 4 potential hybrid orbitals. So it could form more than 4 sigma bonds if it would like to. And then let's still take a look at D here. Sulfur can utilize p-orbitals to form double bonds. Again, that's true. That is a true statement. However, that doesn't explain why sulfur can have more than 4 bonds, because if I go back to oxygen, oxygen or carbon or anything else that has p orbitals utilizes those p orbitals to create double bonds or triple bonds for pi electrons. So that is, while it's a true statement, okay, it is not the best answer for explaining what's going on here when I can create more than 4 bonds for sulfur. It's those d orbitals that are hybridized that really allow me to surpass the octet rule. All right, now number 5, hydrogen is one of the few elements that lacks the ability to hybridize. And why is this? Now I do want to mention here, hydrogen tends to be an exception to many rules. So hydrogen only needs 2 valence electrons to be complete, whereas most other atoms require 8 in their valence shell. Hydrogen is found in a metallic grouping, even though it acts as a non-gas or a non-metal. At very low temperatures, it can start to act metallic. But you find hydrogen all the way over there on the left-hand side of the table with the metals like lithium and sodium and potassium. You would say, oh, I would expect this to be a metal. It's a non-metal. It has higher electronegativity. It's a gas at room temperature instead of a solid. So it kind of violates a bunch of these rules. But there is a reason here, and it doesn't have to do with hydrogen's wacky, exception to the rule sort of thing that will explain this. So let's take a look at these. A, hydrogen only has 1 electron. Again, a true statement, but that doesn't really explain why it lacks the ability to hybridize. So that would be out, even though it's a true statement. All right, hydrogen does not need orbital overlap for bonding. That is a red flag, and that is false. Orbital overlap, whether it's hybridized or non-hybridized, must be present for effective bonding to occur. So again, case in point, think about when you form pi bonds. You require p orbitals to overlap with one another. That doesn't mean that they're hybrid orbitals, but it still requires orbital overlap to form those double bonds or those triple bonds. Orbital overlap is essential in order to create effective covalent bonds. Now, that doesn't mean you always have to have hybrid orbitals, because you can get away with non-hybrid orbitals that have overlap. However, this again is not going to be the best answer here. In fact, this one is definitely out because that is an incorrect statement. All right, C, the p orbitals for hydrogen are empty. Well, there's something a little bit tricky here. And that's the fact that this kind of goes along with option D. Hydrogen lacks sufficient orbital variety for hybridization. The answer here is there are no p orbitals. So for the p orbitals of hydrogen to be empty, that's implying that there are p orbitals to begin with. There are no p orbitals available to hydrogen, and that would make this statement technically incorrect, right? Now, hydrogen lacks sufficient orbital variety for hybridization. This is a true statement because when I look at hydrogen, it only has an s orbital. It's found in the 1s level. When I get to 2s, I have 2s and 2p. And then when I get to the 3rd level, I can have 3s, 3p, and eventually 3d once I pass 4s. And so hydrogen only has an s orbital. It doesn't even have p orbitals, d orbitals, f orbitals, etc. So there's no variety in order to create hybridization. Again, think of the word hybridization or hybrid. It means a mixture of 2 or more things. And so it's the lack of that orbital variety that confines hydrogen to just an s orbital. It can't create any sort of hybrids. All right, so those were the questions. I'm going to delete the board here, and I'm going to bring up a summary that we'll go over real quick. So give me just a second, and then we'll go over that. All right, everyone. So here is the summary table for hybridization. Now, a couple notes. Hybridization is a mixing of 2 or more types of orbitals. So remember, we at least need s and p in order to get sp hybrids. And then we could have spd. You could also have pd. You can mix various orbitals in order to hybridize them, but it requires more than one type, which was like that last question that we talked about with hydrogen. All right, now, this will occur, similar to the second question we asked about why this occurs. This will occur because it's going to allow for better orbital overlap when we deal with bonding, and it's going to lower the energy of the bonding electron. So remember when we drew those energy diagrams, we had the S, we had the P, and then it lowered that energy of the P electrons down, and the sp hybrids were lower in their energy. So let's take a look here. Give me 1 second. I got to correct this. I got to bring up the 3. I'll just write it in here. Okay, so for this This is sp3, this is sp2, and that's sp. My numbers didn't transfer there. All right, so for hybridization, this nice little chart should keep everything organized for us. So sp3 is going to have tetrahedral geometry. It'll have 4 electron domains. And I also want to point out here with sigma, because some people get confused with this, these values here are the maximum number that you are permitted to have in that hybridization. Max. So the most I could have is 4 sigma bonds if I'm sp3 hybridized. Now, what do I mean when I say I don't have to have that? Well, for instance, water is sp3 hybridized. It has 2 lone pairs of electrons and 2 bonds. So there's only 2 sigma bonds present in water. The other sets of electrons reside as pairs, although it is still sp3 hybridized. All right, so this is a maximum limit. sp3 has utilized all your p orbitals, so pi is not going to be an option for sp3. The max would be 0. I can't have any pi bonds present there. Now for sp2, we're dealing with trigonal planar as the geometry. Remember that that's flat, whereas the tetrahedral would be like a tripod type shape. There would only be 3 electron domains total for something that's sp2 hybridized. You could have a maximum of 3 sigma bonds, and the maximum pi bonds that you could have would be 1, because again, we're leaving behind 1 p orbital. The other 2 are being brought into the hybridization. And then we have sp. sp is going to be linear. You would have 2 electron domains present there. You can have a maximum of 2 sigma bonds that are involved with anything that's sp hybridized. And then you could have a maximum of 2 pi bonds present in anything that is sp hybridized. So that's a good little chart if you ever need to go back and reference it. All right, now a couple other notes here. Remember the n-1 rule where n is the electron domains. If you need a quick fire way, especially as you're working on the MCAT questions and you're trying to save your time, the n-1 rule, if you can count your electron domains, will save you some time when you're taking the test. Anything in the 3rd row or below on the periodic table can form more than 4 bonds, and this is due to more hybridization options. So we have d-orbitals, and eventually you have f-orbitals as you get further down into the lanthanide series and things like that. However, what we're focused on right here is that basically anytime you go to the 3rd row or below, you have at least d-orbitals, and you can start hybridizing those in and giving you more bonding options than you would get from just the sp hybrids. Although the sp hybrids, meaning sp3, sp2, and sp, are by far the most common examples that we see and that are utilized. Okay, and then finally, to just remind you, s orbitals are the closest ones to the nucleus, so the electrons that are found there are going to be the most stable, and we go out from there. So the p are further removed than the s in any given quantum level, and then the d are further removed than the p in any quantum level, and so on and so forth. So as we continue to get further and further out with these electrons, they become less and less bound to the nucleus, and that's important to keep in mind when you're talking about the stability of various hybrids. How much S character do they have, how much P character, and how much D character in terms of, you know, the strength of the bonds that are being formed and things of that nature. So that wraps up hybridization. Hopefully everybody found this lecture useful and you feel a little more confident in your hybridization skills. Again, I just want to mention there will be other lectures on Lewis structures and resonance, on MO theory, on things like that. So this is one portion of bonding, which is a very large subject. So thank you for watching, and we will see you guys for the next lecture.